So, now that we have discussed the origin of the phase shift associated with coherence length, let's throw one more cook in the kitchen, and that's the Guoy phase shift. This arises in particular when you've got high numerical aperture objectives. That's when the Guoy phase shift becomes increasingly significant, and we'll see why in a moment. However, the origin of the Guoy phase shift can be fairly intuitively understood, and I just want to make sure that we understand the difference between the Guoy phase shift and the Guoy-duck phase shift. And the Guoy-duck, it is not actually obscene. This is these are impressive mollusks from the Northwest, but not to be confused with Georges-Louis Guoy, from which the Guoy phase shift has its name. All right, so before we consider wave optics, let's go back and take a look at classical phase shift across a focal volume. If we have a wave that has a particular sign for the polarization state, and we transit through the focal volume, then the phase classically, if we forget all about everything we know about wave optics and just ask what does the phase have to do, it has to invert discontinuously in the focal volume. That's problematic because, you know, nature hates discontinuities, but that is the nature of this phase change in the classical limit. So if we start to embrace wave optics and abandon this idea of a classical 90-degree phase shift instantaneously arising in the focal volume, then what we get instead is some necessarily continuous function that changes in phase through the focal volume from 0 to pi. That should be nice and 0, and this should be nice and pi. I like nice pi. It's tasty. At any rate, a continuous function spanning this focal volume, as opposed to this discontinuous abrupt function that changes from 0 to pi right in the focal volume. We know that that really can't exist in wave optics, and so we expect there must be some sort of continuous transition between one phase and another across the focal volume. It turns out in this general expression for the intensity, well, actually for the amplitude as a function of position in both radial and axial position, rho and z, that the key element in this expression is this tangent, inverse tangent term, because that ultimately dictates the phase of the wave between as it transits this focal volume. And that is ultimately the origin of the Guoy phase shift, this e to the I inverse tan z over z0 term. So in the limit of low numerical aperture, it turns out that this phase shift is not particularly important, because yes, the phase has to vary from 0 to pi through the focal volume, but it doesn't have to do so very quickly. So within this focal volume, the phase can vary pretty darn slowly. And within the extent of the crystal, the phase doesn't actually change all that much, as long as the Guoy phase length, the length over which this phase transition happens, is much longer than the characteristic crystal size. If the crystal is small relative to this value, then the fact that this is happening actually doesn't matter at all, because the crystal doesn't know it. Now let's consider what happens instead in the limit of a high numerical aperture objective. In that case, we now have tight focusing, and in tight focusing, this phase shift has to happen over a much smaller distance, and that distance starts to approach the characteristic crystal size of the SHG emission source. And in that limit, the Guoy phase shift cannot necessarily be categorically dismissed. So let's ask ourselves what happens. Well, in the epi direction, it turns out that this doesn't matter one lick, because in the epi direction, the backward coherence length is almost invariably much shorter than the Guoy phase shift distance. And so all of the backward generated SHG is entirely dictated by the backward coherence length. The key is what happens for the transmission direction, because in there we may have potentially competition between the transmitted coherence length and the effective coherence length arising from the Guoy phase shift. So which one will dominate? Well, it's all bets are off. You got to place your odds and see which horse is going to be the fastest. There is no way to a priori predict which of these two effects will dominate, The idea is to simply calculate them and see which one rules. This is just an example with water. Just to give you a sense of, first of all, how significant or potentially insignificant this Guoy phase shift contribution is. In this case, what we're looking at is something where we have a crystal that is, semi-infinite, and we are asking what is the SHG intensity as we transit through this focal volume. And it turns out that the integrated net SHG intensity adds throughout the entire extent of the crystal. It doesn't add quadratically as you might expect, and the fact is it rolls off from this quadratic expectation because of this Guoy phase shift. And that's why we end up with something that sort of asymptotically approaches a value less than this quadratic roll-off. But it's a significant reduction. Fortunately, we have the tools at our disposal to calculate it. The key, though, is that for second harmonic generation, you really do get a net addition of SHG intensity throughout the entire focal volume. I want to just contrast that with third harmonic generation to understand the origin of the surface selectivity of third harmonic generation, which is often touted in explanations of THG. And the explanation typically arises through means that are not obviously clear. I'm not going to provide a clear one either. I'm just hoping to provide a bit of additional clarity. So if we've got, for example, a system that has, considering third harmonic generation as something transits the focal volume, we get addition, but because in THG there's a faster phase walk-off than in second harmonic generation, we really do get this sort of turnover and reduction, this interference. Now in SHG that resulted in a roll-off. In THG that really results in net negative interference and a destructive third harmonic generation response from an isotropic system compared to something that cuts off at the halfway mark and generates a fairly bright signal if we don't have something on the opposite side that also interferes destructively. And thus we end up with, ironically, a effective interface selective third harmonic generation response, although second harmonic generation doesn't have that same expectation. But all of this arises not from the orientational selectivity inherent in SHG, rather from the just plain old geometric optics that describe the nonlinear optical phenomena